everybody, from your favorite artist electronist here, Mr. Q12. I have an important update to discuss here and to present to you as well. And I am pleased and also happy as well because I got a very good result and quite an unexpected result actually. This time with much more better probing and measurement reading than previously. What I did right now, so I changed my ESD 44N, this one, that I was concentrated onto it to test it. I did test the shit out of it, but good enough to give me the direction how to do it right. And the next logical step in the evolution of this entire endeavor that I'm after was to change the MOSFET from, like I said, from that ESD 44, and with this one, this is a SMD one, you are able probably to even read its markings, and not that well. A09T is this marking that is having on top of it. So let me show you here this one, and I have a bunch of them. Usually I'm buying 100 of them, and I have quite a lot of them, and there they are. And it's very little, it's very tiny, it's an SMD like I said. Yeah, okay, yes, perfect. A09T. Okay, so let me put it back, and you may observe that I'm having this little warning paper. This time around, when I work with them, I put this label on all my MOSFETs that I'm having. I'm having here a P channel as well, like that, you see. I had to repair this a long time ago. When it came, this little thing was broken, and now it's repaired and it's working because I know how to melt plastic. It's not that big of a philosophy. And also these motherfuckers who are extremely sensitive, extremely exaggeratedly sensitive to electrostatic discharge. This is what it means. ESD, it means electrostatic discharge. So be careful with MOSFETs with electrostatic discharge, because this is a lesson that I'm always forgetting and is a little bit inconvenient. It's a lesson that I have to practice it more by using a strap, this ESD strap or discharging strap. And I am connecting it actually here. This is my metal table that you can see here is metal, you see. On top of it, I'm having this wood boards, but here is metal. I built this table from various mild steel profiles, L profiles, this tubular square profile, etc., you know, to fit my room. So I'm having this linked here, and this wire that you are seeing, actually you can see the wire here, this yellow wire that is going somewhere there, that is going all around beneath the table like that, and is going here into the ground pin, which is this one, this pin here. And I don't know how to test it for you. Actually I know, but I don't have 7 hands, and show you how I'm checking if I'm connected to ground and not floating. And let me open it, and here is set. I know it's hard to see, but these were some kind of idiots who put this color marking. Here is white, it's supposed to be white, and here is supposed to be yellow, but with time both of them, they got yellow. Mostly this white got into the yellow zone, and they are kind of interchangeable. But this is the line that is separating from 1000 volts, you see, decreasing to constant voltage, and this is alternative here. So I'm setting it to 750 alternative voltage. So this is what I did here, like this, you see. So I connected one of the plugs, doesn't matter which one. If I'm inserting it into this hole, yeah, this is more correct here. 124. This is 25, and connected to the ground there. I should connect this here and this one to the ground. Yes. So this is what I wanted to show you. Well, let me switch it here actually, because this is more correct, but you cannot see it very clearly when I'm touching there. Yeah, 124. Okay. And here when I'm connecting it to my table here in my screw, you see 124. So my table and my strap here, it is grounded correctly, and that's the test that you should do. And right now I just check it, because sometime I discovered this wire just broke some other times ago, and I had to get into there and start rewiring everything and find the bastard. You probably can see, you see it's a connector there, and that motherfucker, before that connector, to that white connector that is there, before that connector I had a very shitty link, and then I decided to add that very easy connector. Well, this is how you verify your grounding. This grounded strap, let me say some words about it. It came with this green mat, and this is a rubber mat, and it's having some kind of paint here, which is very easily scratchable, and you can see the black underneath it if you are not careful. I'm keeping it here for very important projects that I will do probably in the future or never. But from what I understand, this is good enough. Green rubber that I'm having here is an extra protection, and is way more better to have it here than not having here. I know I should have mounted it here, especially for this experiments that I'm conducting right now, but I'm not used to it, and it's kind of in the way I'm working. And my idea is to have this setup like I'm having it here, like this, like I'm used to it to work, and then to have another zone or area where to go and work specifically on this kind of material, specific electrostatic discharge material protection for sensitive components like these MOSFETs. So this is in the future when I will have a lot of space, but right now in my tiny, very tiny room that I'm having here, I don't have that luxury of space and I cannot use all the things that I want to use. Usually I'm adapting to things, but in this case I couldn't adapt. All right, so why did I'm using this strap is because I learned the hard way that these MOSFETs, I was testing these MOSFETs and they were literally burning out with a very red dot and a circle of redness around it like that. That's my MOSFET and that's the red spot that it burned into, either in this right side or in the left side, doesn't matter where, but it did that. And actually it cracked one of them, and also a little bit of smoke, like a string, like that, you know, very fine smoke, psh, like psh, you know, and that's it, dead. I put 100 ohms here, so the amperage that was, the current that was passing through it, it was very, very low, and it still burned out. Fantastic. And I didn't catch the problem from the first time. I was thinking is my setup that I'm having here is the cause, and I was changing all the parameters to accommodate the MOSFET not to burn it. But even at a very high resistance that I was having there, the current, it was extremely low for the MOSFET, and it was still burning. And then I realized, wait a minute, it's this motherfucker is burning because it is electrostatically damaged. And I have the proof here. Let me put this there. So you see, those are another set of dead musketeers. Unfortunately, a little bit too many than my likings, but I learned my lesson a little bit more harder this time. Well, I put those labels here. I put these labels, this SMD label that I know for sure what it means. And this is not my first time. This is my, I don't know, 10th time in my life when I'm having this ESD problem with the MOSFETs, especially with these motherfuckers, 2N7002. They have exaggerated sensitive gate that I use them for a project, actually, for that sensitive gate that they have for a sensing circuit that is using this MOSFET, and I'm having 100 of them. Yeah, you cannot see them, but they are there. I probably used 5 or 10 from them, but I'm having 95 remained. Actually, this is the project that is using that 2N7002. That's the MOSFET there. Let me zoom in. Yeah, you see it? And it is sensitive to my hand, and I built this project in 2019. This is a remote control circuit board here, this longer one, but that's the sensing circuit board, and this is just the display. And this was a very, very old project, and this is what it's doing, is doing this sensing of my hand, and I'm keeping it for a very, very long time. It's having this electromagnet, and I had a bunch of problems with it in the course of the years, and I don't remember what it was. Probably also the MOSFET. I changed MOSFET? I don't remember. Yeah, actually I have here problems. A list of problems. Okay, man. So so the relay didn't turn correctly. So the problem was the soldering. One motherfucker of a transistor, this BC558, that's a 558, that one. One of its pins was unsoldered, and because this circuit couldn't, this is like a filter circuit for the signal that is coming from there is filtered by this one, which was a very late circuit board. That's why it's there. Placed in that position. It should have been in continuation here, but it remained like this. This is a prototype, what you're seeing here. And after filtering is going, the signal is going into the display, pretty much. This chip that you're seeing here is LM3914, you see? And it's doing this, this very nice. As you can see, I have some LEDs that are not lighting anymore. Here, you see? Those are not lighting that branch, and I didn't bother to repair it. But yeah, this is a 555, by the way. So this is good to have a history of it, because you fucking forget all this shit. So why I'm showing you this project is because that transistor, that MOSFET transistor that you are seeing there, that is the sensing element, it's exaggerated, extremely sensitive gate. That all this project is built around it, around that very sensitive gate. That's why I'm showing you this project. With this project, I'm also testing and I'm also proving how long time this particular component, this particular MOSFET is actually in function, is actually working, is actually doing its job as sensitive as it is. But if you don't fuck around, if you don't touch its gate with your fingers or with a brush or anything, this board was never brushed ever in its life for dusting or anything like that. As long as you don't touch it, and specifically its gate, it is working absolutely perfectly for 5 years. So I built this in 2019, like I said, and right now it's 2024. So I'm having exactly, I'm showing you my watch because I'm having also the year there. You see the year is 2024. That's why I'm proving, in a sense, with this project, the longevity and the reliability of this particular MOSFET here. So I cannot praise it more than this. It is a very good MOSFET, but for very special projects like this one, like this sensing thing, and not touch it. If you touch it, you kill it. That's the only rule that I'm very aware of, and I also destroyed a lot of them, quite a bunch of them, until I reached this stable circuit that you're seeing here, and it's doing its job perfectly. Probably one time I changed it in all these 5 years, probably, but I really, sincerely, I don't remember to change it, that specific MOSFET. Probably one time when I was fucking around with my fingers on its coil, this round coil, or directly on its gate there, for some fucked up reason, I don't even remember why. But from then, I learned my lesson and I never touched that area there with my bare fingers and without grounding, without putting my finger on the negative rail and surging my electrostatic accumulation on the skin. Right here I don't have it, but usually you should do it like that. You touch the negative rail and you practically you discharge yourself into the negative rail. That's the idea. And it wasn't that long ago, but this problem that I solved it. But the problem persisted for probably 1 year, and it's because of bumping it. Probably somebody, me or my father, bumped the board here because it is unprotected, and from that bumping this got loose from the soldering. But now it's functioning like it's new. You see, that's the sensing coil there. So enough about this. I wanted to show you the transistor, the MOSFET, why I took those extremely sensitive MOSFETs, and the project that I made with them. For me, it's still an extremely sensitive MOSFET, stupidly sensitive MOSFET to ESD. So the moment you touch, doesn't matter what kind of charge, how low charge or high charge your finger, your skin is, it will get fucked up. It will not work anymore. So these are way more sensitive than this. These are more resilient a little bit, but it turns out these are very, very sensitive as well. So I'm having a history here in my room that I'm always forgetting it, this history, and I shouldn't forget it. That's why I put these labels, these ESD labels there, to all my MOSFETs, not to everything. I have a history with this electrostatic discharge in my room. At some intervals, specific times in the year, it's starting to accumulate more higher and higher, pretty much, the electrostatic charge on everything, including my hands. But not always. That's the problem, because it's like a low and high. Low and high is like a sinusoid, is like that. In the summer is the lowest part when it's the hottest, and the most inconvenient to work is the most wet air. The air is very wet. That's the lowest ESD electrostatic accumulation of particles, of charges, and they don't really affect anything. I am working with the MOSFETs, I'm touching their gates with my bare hands, and they don't get fucked up easily. They don't get destroyed or damaged easily. But in other times of the year, when it's autumn, especially in the winter is the highest peak, the maximum power of the electrostatic discharge accumulation. And I'm getting extremely easily charged up my hand in the middle of the winter when it's the coldest, in the February. Then I'm getting sparks only by doing this. Depending what I'm handling, but sometimes I'm getting sparks on myself. Is like that. Not every time. These are very specific times, very rare occasions, but occurrences. But is getting that high potential. This is a very big problem for a very long time in my room, in this specific ambient that I'm having it here, and it's prevalent here. It's by the book, probably. If someone should write a book about electrostatic discharge, they should live in my room. The problem is in the course of one single year, and you cannot see them that clearly. You cannot catch all these details. These are very fine, minute details that you cannot see them, like everyday life stuff. It's very hidden or covert information that you have to pay extra attention to it. And be very careful with it to actually catch it. And how I catch it usually is by burning these fucking MOSFETs, the new dead musketeers. So I really don't like to burn my MOSFETs or any component, but it happens. And from mistakes, you are learning. Those are burned from other reasons. So it's normal to have dead components when you are testing them. So I am a tester, and I'm doing my best not to burn them. That's my prerogative here. All right. After I discovered that I neglected this electrostatic problem, I immediately put my strap. I connected my strap here and I worked with it, and lo and behold, it started to work normally, because before it wasn't. It was blowing up. Those transistors, I changed them all there, and it was a pain to change them because I'm having a resistor there as well. You see that resistor, tiny little bit resistor between those two pins. It's a pain in the butthole, and yeah, it's not nice, it's not easy, and but I had to do it a number of times, but in the end I figured it out what was the actual problem, and then it worked. And behold, voila, how it's burning. 1, 3, 2, 1. And let's see, voila. Yep, it did burn. I'm not sure if you could see the smoke. So you've seen it and heard it, how it popped and smoked. Fantastic, very interesting. Very interesting. Before I'm starting anything, let me present to you the circuit diagram. that I'm using here. I know it's a bunch of wires here and you can barely understand where the fucking components are. So what I'm having, this resistor, RX I call it, because I change it a lot in the course of many experiments. So this, at this point, is this 10 ohm resistor. And you can see it here on my table as well. This RX load is constant. You see it's 10 ohm all the time because it is that 10 ohms. You see, you can barely see there 10 ohms. This is a probe from my digital thermometer here, and I got the nice idea to actually link and hold all this wire that was dangling all the time here. So it's good to have it like that. That's the resistor there, and which is this, and I'm powering it with a variable power supply. But usually I was testing everything at 5 volts for a very long time, and that's why it remained there 5 volts. But in my list that I'm having here, you see power supply voltage. Actually, this is what I'm varying here, 5 volts, you see 5.00, 6, 7, 8, and that's it. This is the only variable parameter from my power supply, and everything else falls along with this changing, this voltage changing. If I'm having it at 5 volts, everything else after that is listening to this 5 volts parameter that I'm having here. And also here, if I'm changing the voltage to 8 volts, everything else, all its data is listening to this voltage that I'm having here and is accordingly increasing with it. Okay, so this is clear as mud. All right, so that's the voltage here, which is variable power supply 1, which is this one. I have a secondary power supply here, which is an ATX. You see here, ATX power supply number 2. I'm getting a constant 12 volts through this yellow wire and blue wire. You see here is connected, and this blue wire is the negative, and this yellow is the positive 12 volts into this switch, and from the switch is going directly onto the gate of the transistor. And it is what you are seeing here. I'm having this 10 kilo resistor. The MOSFET will remain on if I'm not connecting this 10 kilo, and it's that resistor, that SMD, that you can barely see it there, but it is. That's the gate, that's the source pin, and this is the drain of the MOSFET. You see, drain, gate, and source, and it's exactly like an NPN with a base, collector, and emitter. It's pretty much the same configuration, the same pinout. And also for this MOSFET, I'm having this 10 kilo resistor in the back from the gate to its source pin. All right, clear as mud. And that's it. This is the MOSFET with its internal diode. Another point is that the ATX negative rail, which is this blue wire, is going directly here, connected with this other negative wire, also blue, from my variable power supply 1. These two lines from power supply 2 and power supply 1 are connected together as a common negative rail, 0 volts. Okay, so this is the circuit so far. I didn't show here on the circuit diagram. I should probably show my multimeters that I connected here. But what I did, and probably I should put, but I don't have that much space here. And the circuit is beautiful without all these voltmeters connected. So here and here, in these 2 points, I put 1 voltmeter, which is this one, the top one. So it is connected. If you follow its wires, you see this red wire is coming from him, and this blue wire as well is coming through underneath this one, but it's going directly there onto the pins of the resistor. And you can see the positive line is connected on that pin right on this wire as well, exactly as in my diagram that you are seeing here. This is 1 voltmeter across it like that, and another voltmeter. That's why it's hard for me to add it here from this point to this point, you see, across this transistor. So it's from its source, this red wire, you see, and this drain, and these are the 2 wires from the multimeter here, you see, these 2 and are coming from him. And that's it. That's all the setup. And also my temperature probe, like I said already, over this resistor, because this is the load resistor that is getting all the power across it. And it is heating up fantastically high. And you will see when I will conduct the experiments. And I will go back to 5. There. Come on. There. 5. And I'm powering my ATX power supply here. But the switch is not turned on. I'm having this very interesting issue when my multimeter is reading over the transistor while the gate is off. So practically the gate of the transistor is floating right now. If I'm switching to here, so this is actually okay, it's the 5 volts because the voltmeter is across this and this points, and it's passing only through this 10 ohm resistor is actually seeing that the 5 volts, so it's actually seeing that voltage, and this is flickering like that because it cannot reach higher voltage. This is what it's telling me, it's flickering like this because the voltage is too high for this parameter to read. Okay, all right, so let's conduct the experiment. And here the amperage is 0. I'm also having on my list, so we are here at the first line that you are seeing there. So you see, this is the first line, 5 volts from my power supply, and the amperage will go to 0.47. At least the last time. Let's see what this will bring up. So when I'm switching it on, now 0.48, but if everything will heat up like my resistor there, it will probably go a little bit less, I hope. We will see. So next I'm having, this is the voltage across the resistor, 4.71, Here, voltage across the resistor was 4.64. Why the fuck do I get? Ah, I know. So I have to tweak from the voltage here because a tiny little bit of a changing in the voltage here will change all the parameters that I'm having here. So one second to calibrate it as it was before. Okay, so I tweaked a tiny little bit from here, but I swear that was 5 watts the last time. So now it's 4.9, which I don't like it at all. But at least I'm getting these values that I was getting the last time. 4 volts and 64 there. 4 volts and 65 now. Motherfucker. Anyway, this voltmeter is across the resistor and is this voltage over Rx 4.64. And this other voltmeter, which is across the transistor there, like I said, is voltage over drain and source of the transistor, VDC, and is this 0.0461. But here it's showing 46 because it is at 200 millivolts setup. 46 millivolts, what we are seeing here. If I'm changing, yeah, it's not actually showing 0.046. It should have here a point, 0.045, but it's cheaper to implement it like this probably. Let's see here. Yeah, kind of, yeah, now it's correct, 0.046, but I'm not getting that resolution, that higher resolution like here. So here I can see these 3 digits, that's why I'm keeping it here, 0.0461, and exactly this is the value what I'm getting here, but I have to convert it from this value into this voltage value that I'm having it here, because it will get easy to calculate. That's why I'm converting it here, like that. And this is it, this is all the setup that I'm having. Let me close it. The last thing is the temperature over. Yeah, that's not correct, 97. It's actually way more higher. It's actually 150 degrees Celsius, but I didn't catch a good spot. Last time I was getting 150 when I was probing it manually. Yeah, okay, so in general, in principle, so you see how low I'm here and how low the temperature is. So here on the top is the highest temperature, at least for this resistor. Okay, let's say it's correct. Yeah, 110. But it was 50 actually. You see, it's very, very picky. And now let's see some calculations. And here is my trusty calculator. I'm having 5 volts from my power supply. Okay, so that's 4.9 right now, but it was 5 volts the last time because I am conducting all my experiments quite correctly. For some reason, right now is fucking my movie a little bit. So this is the power supply voltage and amperage, and I had to manually calculate the wattage for my power supply as well. So let's see. So 5 times 0.47 equal 2.35 watts. For the entire circuit that you are seeing here. And this is what the power supply is delivering right now. How much wattage this circuit is sucking from my power supply. And my power supply is delivering all this power to this circuit that is requesting. It's saying, give me all this power. And my power supply is saying, here it is, my darling, take it. I already mentioned that I'm using the same resistor here, this 10 ohm resistor, but I didn't put here the wattage at 5 watts. So it's 10 ohms, but at 5 watts resistor, what I'm having there. I put a marking here as well, right now. So voltage over the resistor is 4.64, and we can see it with this one, and right now it's 4.7 for some reason, motherfucker. Probably my transistor now is stressed, or the resistor, or both of them are stressed, because I did conducted this higher temperature, higher wattage, higher power experiment at 8 volts, and I got over the wattage of the resistor. You see here, wattage over a resistor is 5.65, and my resistor is actually 5 watts. And for a very short duration of time, I conducted this experiment, and probably my resistor and my transistor, both of them are stressed thermically. And probably that's why I'm having a tiny little bit difference of values of readings. Right now, when I'm going back to this 5 volts, I kind of change the metallic structure internally from all that heating, all that power that I was subjecting, both of them actually, especially the resistor. And probably it is the resistor that it give up more than the transistor. In this case, is my flare, my assumption, is my guess here, is what I feel it is more happening to that. So this is 4.7, but the last time I was having 4.64. This is the voltage over the resistor. This is the data over it that I'm collecting there. And the current, because it's a 10 ohm resistor, this is voltage over 10. This the voltage that I'm getting over 10 volts, and is 0.46. So it's the same number as here, but with a 0 in front of it. So I'm moving the decimal here, you see, and it's 0.46, and the same is for all of them. It's practically Ohm's law. Current is voltage over resistance, is 4.64 over 10, and that's why I'm getting this value here for the current. Okay, and I also noted here, if you pay attention, you see it here, current through Rx is voltage over Rx, which is this, voltage over Rx, which we are getting right now, over the value of Rx, you see, over Rx, the value of it, in ohms, the resistance, and equals the voltage, whatever it is, over 10. I put it like this because this is what I'm testing right now, the 10 ohms. And then I'm getting the wattage over this resistor. And this wattage over this resistor, you see here the formula, is voltage VRX times the current. So voltage over the resistor times the current over the resistor is giving me the wattage over this resistor. And it's very straightforward. So you see 4.64 times 0.464, yeah, equal 2.15, you see? and this is the wattage 2.15 that I'm getting over that resistor. Right, so this entire area that I'm having it here, these three columns, VRX, ERX, and WRX, this is only for the resistor here. But here is the transistor, the MOSFET data. I'm getting the voltage over drain source. I'm collecting it with this other multimeter, and I can show you briefly. But just to confirm to you that I'm getting exact these values that I'm getting here. And I'm getting 46.3, and the last time was 46.1. Like I already mentioned, I'm converting this value that you are seeing it here because it's 200 millivolts here, and this is 46 millivolts. And converted here, it means 0.046 and 1 volts. What I get here, it is the correct values that I'm getting from reality. And how I'm calculating this wattage for the MOSFET, because this is the absolute important part of all my experiments. This is what I'm after. I'm after the wattage over the MOSFET, how much power this motherfucker is consuming, and also how much power the load is permitted to consume through the transistor. That's the very important lesson. Everything that you are seeing here is my interpretation of how things should work. I didn't read all of this that you are seeing here anywhere, so it is my philosophy. It is my way of thinking, my mentality, how I'm thinking, how I'm conducting my experiments, basically. Okay, so let's see the wattage over the MOSFET, how I'm getting, how I'm collecting, from where I'm collecting the amperage, the current, to multiply it with the voltage, no, to give me the power. So here is the solution that I found here. Hopefully you can see it good enough. So the wattage over the MOSFET, this one, is this VDS times IRX. So I'm collecting the current through this resistor, this current here, 0.464, times the voltage that I'm collecting over the transistor, over the pins, these two pins, drain and source of the transistor. And I'm getting that value, the power, the real power over the MOSFET. Well, as real as I can. Probably I'm getting a tiny little bit of current loss through the transistor itself. So here, this current through the resistor is actually a little bit less in the transistor itself, but is probably very, very tiny difference from here to there. So let's assume it's the same thing. I should have put an ampere meter for each branch. From here an ampere meter between the resistor and MOSFET, and that's it. Probably only that one. And from here to ground, maybe another to actually see what is coming in and what is coming out. And what is coming in is the current through the resistor, that I can read it on the ampere meter display. And here is the current through both of them, including the transistor. I'm getting the current here displayed on this other ampere meter, but this is too much. Too much, you know. And these values are so little, and you will see. Actually, let me demonstrate that it is true what I'm saying. You see this, the current through the resistor here, through this load resistor, is 0.464, but look what is the current from the power supply is 0.47. You see, this 0.464 is very, 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 very close to the current in the display of the power supply, or probably it's almost the same. Probably this is rounding this value that I'm reading it with extra decimals here. So that's what I'm saying, that the current through all my circuit is the same with the current that my power supply is displaying. Pretty much, with a tiny little bit of a difference, but is absolutely ignorable. At least for this circuit, for this very simple circuit that I'm having here. So getting back to the last point, the wattage over the MOSFET is this current through the resistor, which is the same from displayed on my power supply there, times this other one. Let me actually demonstrate it here with my calculator. Let's take the voltage first. So 0.0461 times current through the resistor, 0.4464. Okay, and equals, you see, 0.021. This is my demonstration. This is my theory, at least. This is how I'm calculating my stuff that I'm having here. And by the way, I asked these questions to my English friend, to my American friend, and they didn't respond anything. And I kind of understand them. I don't like it when they don't respond to me, but I kind of understand them because usually they are saying something when they know it for sure. They are not that used. Is my impression, of course, my very subjective impression. Probably they are not used with this kind of experimentation, with this kind of roller coaster that I'm conducting here, going through shit and getting out from the shit, getting a breath of air, and then going back into the shit, and the wheel is turning like that. This is the way of experimentation, and I know it's not simple. I know it's not easy to conduct, especially when you are alone, when you have absolutely nobody. You are you by yourself, and do your best. And this is my situation that I'm in, and that's why I need some friends to actually give me some responses from time to time. And my impression is that they know for sure, for certain, some stuff, what they know. I don't know what they are knowing, but what they know for sure. And they were tremendous good guides, both of them. They guide me They give me very good directions. Do that, do that, do that. And what is very, very important when you call somebody a friend is to actually believe him. And I did believe these two guys the most. And I did listen their word when they were telling me something. I was considering their advice absolutely 100%. And I didn't, for a minute, I didn't think they are joking. So that's what a friend trust means, at least for me, as I perceive it. I didn't like that they didn't respond lately. Well, when I started the MOSFET experiment, and my belief is that they are inexperienced with this roller coaster of experimentation. It's the way I'm conducting the things. That's why they are a bit reticent. They are a bit, both of them actually. They are staying on their bank and not getting up into this kind of discussion or project very easily. They are very hardcore thinkers, like I like to do, like I am, and that's why we kind of find each other, and we got in the same mentality. Probably is my impression. When I'm calling someone a friend, I really mean it. I know it sounds like I'm making fun or something, like, oh, my friend, but in the same time, I know it sounds like that, but also it is true. It's very true. When I'm calling someone a friend, for me, it's 1 and 0. Either you are my friend or you are not my friend. You are the rest of them. Not really necessarily my enemy, but just the rest of them, which I ignore totally. And they don't matter. But when I'm calling someone a friend, I fucking mean it. And I do. You should be proud to have me as a friend. You should be happy to have me as a friend. Yeah, I have a little bit of the way I'm talking. It's is most of the time is serious, but sometimes I'm making a certain way of fun, but I'm obtaining or making fun of everything. This is it. This is the power testing. This is the power reading that I'm making. So what I want to explain here is the transistor, the MOSFET, is conducting all the current through it to let all the power consumed by the resistive load. So that's the role of the MOSFET. It's not the actual power of the transistor itself, what I'm collecting here, but the most power consumed by the circuit is from the resistor, and I believe this is the correct functionality of the MOSFET. In this particular case, is in conjunction, it is hand in hand with the resistor load. The transistor and the resistor, they are going like this, hand in hand. It's not only the transistor or only the resistor. In this circuit, they are going hand in hand like that. They are dependent, they are synchronous, they are working in synchronicity. This is letting all the power over this, and all the power over this is accepted by the transistor. It's like that, vice versa. I want to point very clearly this very strong connection, like it's only one single component here. So that's my point that I wanted to emphasize. This is my experiment that I conducted here. So this is phase 1 when I conducted the experiment at 5 volts here. Like I said, I'm only varying the voltage, but let's do the other experiment, and I will not go through the 6 and 7. I will jump directly to 8 volts, and for a very brief time, and I will not talk at all, but I will only point where to look, what my display will show, because I will conduct this experiment very quickly, because this is way over my resistor wattage, and I will try to be as fast and short as possible. Okay, ready? 27 is the ambient. So remember, this is for the resistor and this is for the transistor. Okay, it's very easy. That and that and this and this. All right, and you can see this display is changing while I'm turning up the voltage here. Okay, so this is 5, now increasing, 6, increasing, 7 and 8. There. So I'm getting 8 volts and 0.77 amps, and I'm getting over the resistor 7.55 this time at 8 volts. Resistor here, voltage over the resistor 754, and here 752 was, and voltage over drain and sources 75.4, 75.2 the last time. And there is the temperature, which is increasing extremely fast, and I don't want to let it reach to higher temperature. Actually, I can leave it a little bit. No, I don't want. But what I'm showing you here, and let me actually switch it off, and it did switch off there. And now let me turn it on, and it did turn on. So let me switch a couple of more times. So off and on, off and on. And this is at quite a big power consumption what I'm having here. Here is the temperature that is ramping up like crazy. And I will stop the experiment right now and blow some air, especially over that resistor, and close this ones as well. Okay, yeah, it's rising up again because it's like, and it will go down, but it helped a little bit of cooling down. For this last value to actually see it, the voltage 0.0752, times the current 0.752, this one here, equals 0.056, and that's exactly what I'm getting there, which means 56 milliwatts over this transistor, over this MOSFET, while letting this 5.65 watts over this resistor load to operate at. So that's the function of the MOSFET, is letting this resistor consuming all this phenomenal high power over it, while the power consumption over the MOSFET is negligible, I may say, very extremely negligible, as it should be. And that's my point here. This is how you calculate the power over the MOSFET. Okay, this is it. I hope you liked all my experimentation that I did so far and all this data that I collected here. And the next step, I will have to find another resistor higher, way more higher wattage than what I'm having here, more powerful resistor, also at 10 ohms. The biggest problem that I'm encountering right now is the switching of the power supply. My variable power supply is switching from the voltage to amperage at 7 volts and at 8 volts into short circuit mode, because most probably is because my 10 ohms resistor was so hot that from keeping it at 5 volts and at 6 volts here, I keep it a bit too much time while I was conducting all the experiment, while I was noting, putting the values down here. Most probably it got super hot in the course of more than 10 minutes while I was writing all of this and correcting all of this, because as you can probably see, I actually erased a couple of values. I spent a lot of time actually getting all these values and also calculating and also formulating, thinking on the formulas. What the fuck should I use to actually get all this power? So I had to think, and all this thinking cost me time, and all this time, this most probably it ran at 5 volts, it ran at 6 volts, and then it reached very high values of power. I didn't check the temperature at all, probably. I don't remember exactly what I did, but most probably I didn't check it. And then when it reached 7 volts and 8 volts, especially the 7 volts, I was a little bit shocked to my core. Why the fuck it's switching my power supply into short circuit mode? I don't know. But it didn't. Right now it didn't switch to that. My belief, my guess is that when the resistor load is hot enough, is weaker enough, is going down its resistance, probably that my power supply is seeing into the circuit, and by lowering its resistance through heating, my power supply is seeing 9 ohms, 8 ohms, 7 ohms, 6, 5, and 1 ohm. And when it's seeing low enough resistance, then it's switching to amperage mode. And I don't know what is that threshold when it's switching. Probably it's 5 ohms. Definitely it is 1 ohm, because I tested the shit out of it, and I know for sure it is 1 ohm. It is switching to amperage mode, into short circuit mode. And that is problematic. It shouldn't switch, because when it's performing that switching, is introducing a very high pulse, a very high amperage pulse into the circuit, and is destroying the MOSFET. That's the problem with it, especially if the MOSFET is switched very rapidly. But if the MOSFET is just conducting like I'm keeping it here in this circuit, probably it's fine to get into the amperage short circuit mode. So that's a problem when I've seen it. But right now in this experiment, probably everything was cold enough. The resistor value was seeing by my power supply sensors, was seeing it as 10 ohms, as it should have been. I didn't let it to heat up too much, and that's why I didn't switch very quickly. Like I told you already, I got 150 degrees Celsius at some point, and I'm not kidding. So that's why at 150 degrees, probably the resistance got extremely low, at least what my device was seeing, and that's why I switched. Okay, enough about this part. But I started with something, and I probably didn't finish it. The next hard part in this circuit, the next step in this circuit to do, is to find a way of increasing power that I'm having right now, because this is the knife on my throat right now, is the switching of my power supply that is switching into short circuit mode from voltage to amperage. And when it's doing that, it is not good for the MOSFET. It is burning the MOSFET, and I cannot conduct all my experiments in that short circuit mode. That's the knife on my throat right now. That's the biggest problem that I'm having, that I'm facing, and that I'm fighting with at this point in this circuit that I'm having right now. This is the biggest problem that I'm thinking about, how to fucking increase the power, but my power supply should not switch like an idiot into short circuit mode. And probably, like I said before, probably I will have to change this resistor somehow. I have no idea how. Really, I really have no idea how. But I will see how. Yeah, I will have to think more hard on how to do it, or even if I will even use this variable power supply anymore in the future. Probably I will have to change it to something that will not have this short circuit mode switching, and that will conduct no matter what. It will get destroyed, but it will still conduct. It will do its job without smart switching. That's my plan. That's the next step that is in plan to raise even higher the consumption, the power consumption over my testing resistor load that I'm having there, and the conductivity, the conduction of power. I'm saying it's conduction of power, but it's actually conduction of current through this tiny little bit of the MOSFET, and I'm very proud of it. Actually, I'm very proud of it. That is conducting this 56 milliwatts and is letting pass. Yeah, not that much current, but it's yeah 0.75 amps. It's very interesting that I could reach to this level with this little MOSFET, and I can see he can lift very high weight on his tiny little shoulders. Okay, this is it. Thank you very much for watching, for listening, for understanding everything that I explained here, and I hope you are leaving from all my movies that I made so far with an interesting and way of how to do it, you know, more clearly than before. I really hope so, because that's my intention. I want to show, first of all, how I'm doing things, how I'm doing my experimentation, my roller coaster through shit, and taking a breath of air and then back to the shit, making exception of me showing how I'm doing things. I want to show how you should test your MOSFETs that you have in your arsenal. Doesn't matter what you have, and what to expect. That's the most important thing that I never ever seen anywhere on YouTube. Everywhere I search for this particular details that I'm showing you here, and I got together and I got onto this road of power searching, of power researching, and I never seen this stuff shown or explained clearly and directly like I'm doing it here, with exemplification on the circuit diagram directly explained, and you know, just not beating the bush with another bush. So that's the thing that I wanted to show here, how to conduct this experiment and what results you should expect and what you should look for. You should look for that, and looking there and there and there, and you should look with one eye there and one eye there. And I really hope I am helping someone there, and someone like me, that it was in the dark, like everybody else on this planet. Like 99% on the people on this planet, they don't know what to expect from MOSFETs. Only a certain few people know this stuff. They know it very well, and they play with it. And I want to play with it, and you want to play with it. And why not having this information explained already and clearly? And it's a mystery for me, and I don't want to remain a mystery. I want it very well put out there, and also disseminated, spread this kind of information, to be spread and told and taught a bit more broadly to more people, to actually be able to test their components and to know what to expect from them, how the behavior should be. Bye bye from your favorite artist electronist here, Mr. Q12. Also leave a like, please, because this is all that I'm asking. I'm not, as you can observe, I'm not introducing any kind of advertisements in my movies. This is a free movie for free people, independent people, capitalistic people, that they believe to their core into their capitalist ways. Capitalist sabaka. Yeah, I really wish I was making money with everything that you are seeing here, but unfortunately it is without any kind of payment. What I'm doing here is purely by curiosity, and because I want to do it. Nobody put me to do this stuff. I want it to be, this information to be open, to be shared, and to be explained, and to be visualized, and to be seen. And that's my motto, that's my directive, that's my programming, if you want. You know, that's how I'm thinking and how I'm conducting my business. My friend said, let me actually pin this here. Pin it like that. And make it a little bit smaller, like that. Okay, so my friends, I question your data. In none of the tests does voltage Rx plus voltage drain source equals voltage from the power supply. And this is my reply to him. Let's see, for 5 volts, and I took each value, each voltage from my variable power supply, and I've added these two values. And it is a very good point that he is raising, actually, and I praised him. You see here, a good eye. I didn't stop to think on this part while I was doing all of this, and probably I should have checked this, yet another detail in the grand scheme of tests. And I should get used to checking this particular one as well in all my tables, mostly as an error, because this is an error that I'm getting from the circuit, just to test how big the error is. So from the variable power supply setting and the difference of voltage, and my excuse and what I believe it's possible. Yeah, so it is a bit low. This is my answer to him. Perhaps some wiring resistance. I did use some small diameter wiring in some places. Connection resistance, small losses that I'm used to already. But it is not sky high difference. Is acceptable losses in my book. So usually I'm using very thick wiring everywhere where I can. This thick wire here, well, this is not that thick legs. And here is a very thick wire also, but here it should have been this red wire here. It should have been way more thicker wiring, and also this other one. So this is going to the drain, and this is coming from the source of the transistor. These two wires should have been
more sick. This is the questionable data that he is saying. It's probably, most probably, is because of this a bit too thin wires that I forget them there. This is another interesting data to have it written down and calculated in my table here, just for error checking. Another interesting point is that I never opened a resistor like this. This is the first time when I'm seeing one inside it, and it's actually another resistor. It's literally a nichrome wire wrapped around a ceramic body. That tube, that white tube, is a ceramic body, and these are the caps for the legs, and that's it. And the wire is between these caps and wrapped around it. Very interesting detail that I wasn't aware about. That's why I was getting all the heat here on the top of the resistor. If you remember, I put my probe here on the top, and while here on the bottom, it was substantially lower temperature. All right, thank you very much again. Bye bye from your favorite artist electronist, Mr. Q12 here. See you on the next video. Next time, when probably I will make a bit more power to drive through our switching MOSFET there. Thank you very much. Bye bye.